started. And we'll continue with our discussions on MOSFETs. Today, we'll be looking at a little bit about PMOS because till now we have been only looking into NMOSFETs, right? The N-channel MOSFETs, which means that the source and drain, both of them are N-type semiconductor, whereas the substrate that we started with is a P-type semiconductor. So if you remember the structure of the NMOS, let me draw it with a different color. If you remember the structure of the NMOS, you know that the source region was N, the drain region was also N. The body was a P-type silicon. So the silicon that we started with would be a P-type silicon. And then you can ion implant N-type dopants into these specific regions to create the MOSFET. So I'm not going to talk about how the device is actually fabricated. That's a class that you can take on device fabrication, and you'll know how the MOSFET is actually created or how you do the ion implantation to create these N-type source and N-type drain, and then how do you create the gate in between. Now, for an N-type MOSFET, of course, you'll apply a positive voltage at the gate so that you attract electrons from the bulk as well as some of these electrons from the source and drain regions. And your goal would be to create a N-type channel just below the gate. Originally, it was P-type because it was all P-type silicon in between the source and the drain. But now, as you are attracting more and more electrons, remember P-type silicon means there are more holes. Now, as you are attracting more and more electrons, effectively, you can think that when there is a lot of electrons just below the gate, effectively that region becomes similar to N-type. And that's when you have a bridge from the source to the drain, and everything is kind of like an N-type material, right? So that's what happens for an N-channel MOSFET, or in short, we call it NMOS. Now, for a PMOS, it will be exactly the opposite, and that's what we'll be taking a look at today. That will start with the N-type silicon, and then your source and drain regions will be P. And then you are going to apply a negative voltage at the gate or a negative gate to source voltage. So in the previous case, for when we were discussing NMOS, remember that we were talking about the gate voltage, but we kept our source potential to ground, right? So we kept our source potential to ground and then talked about a positive VGS. That means you'll apply a positive voltage at the gate. For the PMOS, you're going to apply a negative voltage at the gate. Oops. So you're going to apply a negative voltage at the gate. But what that also means, in a similar manner as NMOSes, the negative voltage at the gate really means a negative VGS. The gate to source voltage will be negative. And for the NMOS, what you wanted to have was this VGS greater than VT, so that the transistor is on. And then the second condition that you wanted for the transistor to be in active or in the saturation region is that your VDS, the drain to source voltage, needed to be greater than V overdrive. And remember that V overdrive is nothing but VGS minus VT. Okay. So those are the two conditions that we had used for an NMOS, and when we wanted the NMOS to be in the active region. And we know that in that active region, the equation for current for the NMOS is going to be ID equal to K times V over V squared, or K over 2 times V overdrive squared. Okay, so that's going to be the equation for your drain current for the NMOSFET in saturation. That's what we learned till now. So what is going to happen for a PMOS is that in a very similar fashion. So now remember that the PMOS is just a dual of the NMOS. So basically, if you're applying a negative voltage at the gate, you're attracting the holes, the positively charged holes. So electrons were negatively charged, but you have these positively charged holes that you're attracting from the bulk region, as well as from the P-type regions at the source and the drain. And you're effectively trying to create a P-type channel between the source and the drain, right? So you're effectively trying to create this. But as I had told you, that the PMOS is basically going to be a dual of the NMOS. So whatever we have learned for the NMOS, we are going to apply a dual of that for the PMOS. And to start with, and I'm going to explain what that duality means for the PMOS. To start with, what we are going to have is that for the NMOS, we connected the source to the lowest potential in the circuit, which was our ground. For the PMOS, we are going to connect our source to the highest potential of the circuit, which is basically our VDD. So this is going to be your VDD, and this is your ground. So that is going to be connected to your source. So this is the source, and this is the drain again. And this was again, it was the source, and this side you had the drain. The way it works, we have already explained that you are attracting these holes, which are positively charged, toward the channel to eventually create that bridge between the source and the drain. And of course, in this case, the source will be a source of holes because you're going to create a p-type channel. And drain is going to be a drain or a sink for the holes. Now, if holes are propagating from source to drain, the current flow is also from source to drain. In the previous case, the current flow was from drain to source. So again, remember that there is a duality here, that the current flow in the previous case was from drain to source, whereas in this case, the current flow is from source to drain. And that's just because the source is always the source of the majority carriers. So for an N-type MOSFET, your source was source of electrons. So electrons flow from source to drain. That means current flows from drain to source. For the PMOS, the holes flow from source to drain. That means current also flows from source to drain, because holes are again the dual of electrons. Okay. And that also gives you the idea that why we connected the source to the highest potential in the circuit, to VDD in this case. Okay. On the other hand, for the NMOS, when we are doing the analysis, in most cases, except for the scenario when you had the source regeneration, but you saw that the source was going to be connected to the ground, right? Remember your common source configuration? Your source was grounded, your gate was the input, and your drain was the output, right? So similarly for the PMOS, your source will be connected to the VDD so that the current flows from the higher potential to the lower potential. Again, remember, current always flows from higher potential to a lower potential. So we are not violating any of those rules that you had learned till now. Current flows from higher potential to lower potential. The same thing happens here as well, because the source is indeed at a higher potential. It is at the highest voltage of the circuit, which is the supply voltage or the VDD. And in this case, current used to flow from drain to source for the NMOS, and the source was connected to the lowest potential of the circuit, which was the ground. Now, in terms of the equations, I'll again go through the details. I have the notes that are uploaded on Canvas. I'll go through them. But before that, I just want to very quickly talk about how you should think about the equations for a PMOS, and that will make things very clear. So the negative voltage that we talked about at the gate, that really means that you have a negative VGS, right? You have a negative VGS for the PMOS. This is the PMOS, where you wanted to apply a negative voltage at the gate. That means you have a negative VGS. And that also makes sense, right? Because source is connected to the highest potential of the circuit, which is VDD. So now you apply something that is smaller than that. Of course, highest potential of the circuit is the highest potential of the circuit. Anything else that you apply at the gate will be at a lower potential. And if that happens, your gate to source voltage is going to be negative, right? And it was positive for the NMOS, it is going to be negative for the NMOS. But the threshold voltage, remember that we had that concept of threshold voltage, and what threshold voltage really meant is that as you are attracting these minority carriers from the substrate, from the bulk, at some point, your channel will be as much N-type. So let's talk about the NMOS first, and then we'll talk about the PMOS. So for the NMOS, for the top figure, you wanted to create a channel. And when do you say the channel is formed? When your gate to source voltage is equal to your threshold voltage. And what does that mean? That the channel region was originally a p-type silicon, but you are creating an N-type silicon instead of p-type. So how much ever concentration of holes that you had initially, you want to create the same concentration of electrons in the channel just below the gate to call that I have reached my threshold voltage. So the channel was originally p-type. That means there were more concentration of holes. You want to create more concentration of electrons, but by the same amount. So when we say more concentration of holes, it was probably, let's say, a particular number of holes per, let's say, unit volume. And you want to have the same number of electrons per unit volume in the channel when you say that the channel has been formed. And that is another definition of the threshold voltage, coming from a device physics point of view. As a circuit engineer, we are very much comfortable in looking at voltages and currents. And then we defined our threshold voltage. Remember that when you plotted your VGS versus ID curve, your gate to source voltage versus the drain voltage curve, it looks like this, similar to a diode as well. And we defined that, okay, after some point, my current increases exponentially, and I defined that point as my threshold voltage. So that's from a circuit designer's point of view. A device engineer will define the threshold voltage as that much amount of gate voltage that you need to apply so that your channel becomes as much N-type as it was P-type before for the NMOS. Similarly, for the PMOS, you want the channel to become P-type, but originally you started with an N-type silicon, so the channel was N-type. So you want to have as many number of holes in the channel as the number of electrons that were originally present in the channel. And you want to do that by application of that negative voltage at the gate. So your threshold voltage in this case is going to be negative. However, the trick is that because this is a dual, while you are doing as a circuit design engineers, eventually you're interested in those equations for ID, VGS, VDS, and so on. And those equations are going to remain exactly the same if we follow a simple trick. That because the PMOS is a dual of the NMOS, we're just going to take the absolute values. So we are going to write down the equation as the absolute value of VGS is going to be higher than the absolute value of VT. That's the condition when your PMOS turns on. Okay. And of course, your VGS is a negative voltage. So the positive voltage would have been VSG. But if you write it down in this way, what it really means is that the negative voltage in the VGS has to be lower than the negative threshold voltage that you would have needed to create the channel. And if you're more negative at the VGS, then your transistor is on. But if you take the absolute value, then of course you need to be more positive than the threshold voltage in terms of the absolute value of the VGS, which was exactly the same equation for the NMOS, but without the absolute sign, because VGS was already positive and VT was also already positive. In this case, the only difference is that your VGS is negative, your VT is also negative, but the equation remains same if we just take the absolute values. That's the only trick that you need to follow when you try to analyze PMOSs as compared to NMOS. But remember that everything is just the opposite. If it was VGS for an NMOS, which was a positive quantity, for the PMOS, VSG will be the equivalent positive quantity. So if you don't want to I myself sometimes used to get confused when I was a student that should I take VGSG or should I take VGS? How do I analyze this? Then I figured out the easiest way to analyze or the easiest way to remember is that just take the absolute value. So you apply the exact same formula, but apply the formula with an absolute value. And this is something you can generalize as well, that whenever you remember that formula, always remember that the formula has absolute value. If the value is already positive, the absolute value is still positive. If the value is negative, the absolute value makes it positive. So you can always remember that the original formula or the general formula for both NMOS and PMOS is that the absolute value of VGS is going to be higher than the absolute value of VT. And in that case, the transistor will be on, irrespective of whether it's a PMOS or an NMOS. Okay. Similarly, when I write the second equation, that is the equation for your saturation region, what I'm going to write is that VDS absolute value, if that is higher than the absolute value of V overdrive, then your transistor will be in the saturation region or the active region. Okay. And what is going to be your V overdrive? Your V overdrive is going to be the absolute value of VGS minus the absolute value of VT. So wherever you had a quantity, VGS, VDS, V overdrive, VT, everything becomes absolute value. That's it. So your V overdrive, absolute value, is the absolute value of VGS minus absolute value of VT. Again, a very generic formula for both NMOS and PMOS, so that you don't need to remember them separately. And then finally, the equation for ID, the absolute value of ID is going to be you can think about K also as a positive or a negative number, because the mobility, if you represent the mobility of electron to be in the opposite direction of mobility of holes, that's generally not done. But let's say your mobility of holes is given in terms of positive or negative. Instead of saying that it's a mobility of holes versus mobility of electrons, then you can consider the absolute number. Otherwise, it's always a positive number. So you have K over 2 times absolute value of V over drive square. And you know K is going to be mu times COX times W over L. And all of those are positive numbers. So that's the reason why we are not taking the absolute value here. But you can take it. It doesn't hurt. Right? So that's the only thing that you need to remember when you are analyzing PMOS. And that's why we spend so much time in analyzing NMOSs, because analyzing PMOS is this easy. So whatever you do with NMOS, do the same thing, just take the absolute value. Okay. All right. So I'll give you a few seconds if you're taking notes, and then we'll get started with the discussions today. And in the meantime, next week there are no labs. But if you want to spend more time on any of the previous labs, you can do that. Just let your TAs know. They will be present during the lab hours. So it's kind of like a makeup session for the labs. Also, if you have any questions related to the homework or general questions related to the course, please make sure you ask those questions to your TAs. So next week is kind of like a makeup session. Yeah.
I saw that you don't have labs on the Veterans Day, but I think lab is still staying that day, at least
yes, that's a good question. So November 11th is a holiday, right? Yeah, so we are not going to have labs as well on that day. So that lab will be shifted to the week after. Okay. So November 11th is a Monday, I believe.
Or
Tuesday, right? So that Tuesday's lab will happen in the following Tuesday. So just make sure that you attend your lab sections like with that in mind, that the lab section on November 11th will actually happen on November 18th. So that will be your lab 6. And then lab 7th will be the following week. But the following week is already a holiday, right? If I remember correctly, it's the Thanksgiving week. So basically what is going to happen is that because Veterans Day is a holiday, November 11th, that lab section, whatever lab sections you have on the Tuesdays, that will get delayed by 1 week. And then because Thanksgiving holidays, that week there is no classes. So only the Tuesday labs will happen after the week after the Thanksgiving. So I guess December 1st week or the November last week, whatever that week is, let me just clarify. Right. But then I think you have holidays starting from 20th, right? If I remember, I don't remember the UF holidays, but let me check now. Yeah, all right. So this is what I was talking about. That okay, you'll have a lab 6 officially is going to start from 10th of November, and this week is supposed to be lab 6, but because November 11th is a holiday, you will miss whoever has that Tuesday labs. Questions?
So you're saying for Tuesday labs,
lab 6 will be on November 18th, and lab 7 will be on December 2. Right? So just like follow whatever weeks we have left in the calendar. So because we are starting our lab 6 this week and lab 7 this week, so all the other groups except for the Tuesday group will finish their lab 6 on this week, November 10th to 14th, and lab 7 during the week of November 17th to 21st. But only the Tuesday classes, they will have their labs on December 2, the final lab on December 2. Lab 7. Because Tuesday you have to shift by 1 week, right? Because there's no Tuesday lab on 11.
That'll make sense. Thank you.
Okay. All right. All right. So let's take a look at PMOSs. So again, as you see that the notes in the notes I have provided, you are always going to be using the absolute value of the voltages or currents that you had learned till now. So your overdrive, you'll just take the overdrive absolute value, and that's going to be your absolute value of VGS minus absolute value of VT, or you'll see VGS minus VT, take that absolute value, it will also be the same, which is going to be equal to square root of twice ID times K, and again take the absolute value of ID, because the current is going to be negative as the current is in the opposite direction for a PMOS as compared to an NMOS, right? Just so that you know about all the different types of symbols that people can use for NMOS and PMOS. So this is all the N-channel MOSFET symbols, all the P-channel MOSFET symbols. Generally, what you'll see these days are these last two symbols. It's a good idea to know about all the other symbols because, for example, sometimes LT Spice uses one of these top four symbols, right? The Spice simulators, as those simulators had been designed, let's say 30, 40 years back, they used a symbol which is a little bit outdated. When we teach about circuits, or if you are using cadence tools, which are much more modern, I would say, they are only using these last two sets of symbols because this is much more simplified. That you have an NMOS when your current flows out of the source because current is flowing from drain to source. If you have a PMOS, your current is flowing from source to drain, so your current is flowing into the drain. So that's what you use for modern symbols of NMOS and PMOS. But these previous symbols also existed for the last 30, 40 years. You should just know that they existed and just look at them. But in the modern tools, you'll only be finding these last two version of the symbols. Although your LT Spice is not a very modern tool, and that's why you'll see the previous symbols there. Yes, question. How does that B terminal work, the body terminal? Excellent question. So let's talk about that a little bit. But before that, I'll just like to mention one more thing, one small thing, that in digital electronics, people have made it even more simpler. Right? So this is what we learned in this class. And in this class, we are mostly learning about the analog behavior of the MOSFET. What do we mean by analog behavior? That voltages and currents are continuous. Right? It's continuous in time. Also, it's continuous in the value. Your voltages and currents are continuous both in time and value. In digital electronics, if you're sampling the value in specific time intervals, then your time is not continuous, time is discrete. You can also quantize the amplitude. You can have a 0, which is a low amplitude, and a 1, which is a high amplitude for the signal. Then you're quantizing or discretizing the amplitude as well. So both in terms of time and in terms of amplitude, digital is quantized, and it's much more simpler. It's much more simpler just in terms of the behavior of the MOSFET, but of course you can implement a lot of algorithms in digital. That's where the complexity comes in. So in digital, people have simplified the symbol of the MOSFET even more, that the NMOS just looks like this. And because we said the PMOS is just a dual of the NMOS, and I don't need to remember which direction the current flows, I'm only interested in zeros and ones and more high-level logic. What I want to do is that just have a bubble in the front at the gate of the device that will say that this is a PMOS device. So this is a PMOS that is used in digital, and this is an NMOS that is used in most digital circuits. So if you're reading a book on digital electronics, you'll mostly find these last two symbols, the last row over here, as NMOS or PMOS. Okay, now the question is, how does the body terminal work? And why is it even there? Right? So again, let's go back to NMOS, and I'll draw that same figure once again, that you have N-channel, N-type source, you have an N-type drain, and you have a gate in between. And let's say you have this oxide layer at the gate, and so on. Now, for the NMOS, current flows from drain to source. So let's say my source is grounded, and I have a higher voltage at the drain. I also have a positive voltage at the gate. to make sure that the transistor is on. Now, in general, in this case, you'd want to have the body terminal grounded as well. So that's what you see in, for example, some of these symbols, that your body and source, they are connected together. And if source is grounded, the body is also grounded. Because body to source, then there would be a zero potential. And remember that the body is a p-type silicon. And the source is an n-type silicon. So if both of them are grounded, you have that PN junction in zero bias condition. So there, the PN junction has almost no effect because it is zero biased. On the other hand, the PN junction between drain and body, so this was source and body, the PN junction between drain and body, that is reverse bias. See, because you are applying a positive voltage at the n-type material and you are applying ground, which is a lower voltage as compared to that positive drain voltage on the p-type material. So the PN junction over here is reverse biased. And if that junction is reverse biased, of course, you'll not see any kind of PN junction behavior. There would be no current flow between the p-type and n-type devices or p-type and n-type material. On the other hand, if you had made that junction forward bias, let's just imagine for a moment that I am applying anything other than ground potential here. If I'm applying anything other than ground potential here, what would happen is that, let's just say I apply VDD over 2. Let's say I apply VDD over 2. So if my VDD is 5 volt, I'm applying a 2.5 volt on the p-type silicon. Now you have your source, which is this n-type silicon, which is grounded. So the PN junction at the source side, on the left side of the screen, the PN junction becomes forward biased because this is a higher potential and this is a lower potential. So this PN junction, p-type silicon to n-type silicon, that becomes forward biased, and you start seeing a forward bias current in this direction, which has nothing to do with the operation of the MOSFET. So what it will create is that there would be an additional current flow, there would be an additional power consumption because of that, the MOSFET will start heating up because of that, and all of those things are unintentional, right? You never wanted that. You're not achieving anything by having this p-type silicon connected to a positive voltage, right? But if you have this p-type silicon connected to ground, clear this. If you have this p-type silicon or the body bulk region connected to ground, then you do not have that problem because your PN junction diodes are never forward biased. And that is the reason why you will see that the body terminal, in most cases, there are exceptions as well, and we'll talk about those. In most cases, it is connected to source so that there is no body effect. The impact or the scenario that those PN junction diodes turn on and create a forward bias voltage from the p-type to the n-type silicon, that is called a body bias effect. That if you bias the body in any other potential other than this ground over here, then you'll see that body bias effect, and there could be a small amount of current flow because of that, which is non-ideal. Okay. And that is the reason why in most cases, for example, here you see that the source and body is connected. Similarly for the PMOS, so this is for N, because you already know that the PMOS is a dual of NMOS, what would be the connection to the body terminal for a PMOS? Or what do you expect? Where do you expect the body terminal to be connected for the PMOS? If source is connected to VDD, and this n-type silicon that you have over here, that also needs to be connected to VDD, right? So the source is here, the drain is on this side, your current flow is from source to drain. This is VDD, the source terminal is at VDD. The body terminal should also be at VDD so that the PN junction diodes do not become forward biased. So again, that is the reason why you will see that the source and the body terminals will be connected together for most scenarios for PMOSs. All right. Now, as I said that this is for most scenarios. That means that there are scenarios where it will not be connected. And what is the advantage of that? Before that, there is a question. Yeah. Yeah. No, that's not true actually. So I would rather say so the question is the MOSFET is a reversible device. So what we said in the beginning is that you can choose any of the terminal as your source and the drain, and it does not matter which one you choose as your source and the drain. I'll still stick by that comment. Why? Because whichever terminal you connect to the ground, that becomes your source. You could have chosen the right side to be connected to the ground. There's no obligation that I have to connect the left side terminal to the ground. Whichever terminal you connect to the ground, that becomes source for the NMOS. Whichever terminal that you connect to the VDD, that becomes the source for the PMOS.
Most MOSFETs have their body terminal connected to one of the two already.
If the body terminal is connected, then it is not reversible anymore, right? Because if you're physically connecting to either left or either right, the body terminal is physically connected to either left or right, then of course that terminal needs to be the source. Yeah. Okay. But as a designer, we are designing MOSFET-based circuits here, and at some point, for example, the follow-up course to this will be circuits 2, then analog IC1, where you can design each of these MOSFETs yourself. They would be nanometer scale devices. There will not be a big centimeter scale MOSFET that you buy from market. It will be a nanometer scale device that can be on an IC, and there you have your full freedom. You have as much freedom as not choosing to connect the body terminal to ground or not choosing to connect the body terminal to VDD as well. You have the freedom to do that. Why? And why would you want to do that? Let me tell you a little bit. If let's say I have, so in this case, what was my goal? My goal was that I would be attracting the electrons from the body terminal. I'll try to attract these electrons from the body terminal, and then I'll try to create this N-type channel between the source and the drain. Now, if you apply a negative voltage at the body terminal, and negative with respect to the source, okay, because your source terminal is grounded, let's say, negative with respect to the source. If you apply a negative voltage at the body, you will push those electrons which are close to that negative terminal, which are close to here, you will push or repel those electrons so that more and more number of electrons go to the channel. And that helps in terms of reaching the threshold voltage, right? You'll reach the threshold voltage at a lower potential because you're already getting electrons repelled from the bulk, as that bulk has a negative potential over here. So you can play around with that as well, that you can make your bulk terminal or the body terminal negative so that your threshold voltage can be changed. You can manipulate your threshold voltage by applying a particular amount of voltage on the body. So this is called body biasing. Your threshold voltage can be manipulated by body biasing. Again, it's a very advanced concept. We're not going to talk about, or I'm not going to ask questions related to that in exams here in this course, because this course is mostly about the simple things about MOSFETs. And you have already seen that there's a lot of content, even if we talk about simple things, right? So I'm not going to burden you with body biasing in this course, but just so that you know that this can be done. So if you're interested, we can discuss more. Similarly, you can choose to not to connect this body terminal of the PMOS to VDD. And you can choose to play around with that threshold voltage. Also, I mean, just like I said that you can apply a negative voltage over here, you could have also applied a small amount of positive voltage here, because any PN junction, you know that the PN junction does not turn on immediately. There is a threshold voltage for the PN junction as well, which is probably in the range of, let's say, 0.6 volt or 0.7 volt. So if you're applying a very small voltage, let's say 0.1 volt, 100 millivolt here, that does not reach the threshold voltage. So your PN junctions do not fully turn on. Of course, there will be more amount of current, leakage current, but they do not fully turn on to create havoc or create basically thermal runaway issues in the MOSFET. But again, you can play around with your threshold voltage. If you're applying a positive voltage at the body, you will be attracting some of those electrons back to the body terminal, which means that it will be harder for you to create that channel. Or in other words, you have to apply more and more positive voltage at the gate to create the same amount of channel. So you can increase the threshold voltage. You can also decrease the threshold voltage by applying a body bias. Again, more complex concept. We are not going to talk about that, but make sure that you know that something like that can be done. Yeah, think about it. The equations are going to be complex, but the idea or the concept is still pretty simple. All right. So here I write down the same equations that we just talked about. That you can write down your ID equation as k over 2 times VGS minus VT whole squared for NMOS. For PMOS, it's going to be minus of k over 2 times VGS minus VT whole square. And of course, if you are taking the absolute value in each case, then you do not even need to think about which terminal is at a higher potential, which terminal is at a lower potential. You can just apply the formula of ID or absolute value of ID is going to be half of k times absolute value of VGS minus absolute value of VT whole square. Right? So that would be same for your NMOS and PMOS. So I'm not going through all of this again. This is exactly same as what we discussed in the beginning of the class. Maybe let's just take a look at one or two examples, right, which will make things clearer. So let's say I still have an NMOS over here. Right? You see that this is an NMOS device. Let me zoom in a little bit more so that you can see clearly. So the first one over here, you have an NMOS device. And I know this is an NMOS because the current flows out of the source. If it is a PMOS, current will flow into the source. VT is given to be 0.7 volt. V overdrive is given to, so you know that there are three different formulas that you can use. But let's say, okay, let me see what are the other things that are given in the problem. Okay, so it looks like it's V overdrive that has been given in the problem, and V overdrive is given to be 0.3 volts. VGS is also given to be 1 volt, that your gate is connected to 1 and source is connected to ground, which is 0 volts. So your VGS is 1 volt, V overdrive is given to be 0.3 volt, and VT is 0.7 volt. So of course your VGS is higher than your VT, or so you can say absolute value of VGS is higher than the absolute value of VT. Since this is an NMOS, those are positive anyway. Now the transistor will be in active or saturation region. If your VDS, and we're writing as VD because we know that the source voltage is already 0. So, but the more general form of the equation is VDS greater than V overdrive. So if your VDS or absolute value of VDS is greater than the absolute value of V overdrive, then you know that the transistor is in saturation. Your absolute value of V overdrive is 0.3 volt. So if your VDS is greater than 0.3 volt or VD is greater than 0.3 volt, then your transistor will be in saturation. So that was the simple one, like very simple scenario. Now let's look at this case where there is a 2 volt connected at the source of the MOSFET. You have the VD connected to the drain of the MOSFET, and at the gate of the MOSFET, you have 3 volts. So your VGS, your gate to source voltage is how much? VG minus VS. VG was 3 volts and VS was 2 volts. So you have 3 minus 2, that is 1 volt. V overdrive is still 0.3 volt. It's the same same scenario as the previous one, let's say. Now again, you're going to be in the active region if your VDS is greater than, or absolute value of VDS is greater than V overdrive. But in this case, see, your source is not connected to ground. So to know what is going to be my VD voltage, you may have to break this down. So I may write it as VD minus VS needs to be greater than VGS minus VT. So needs to be greater than VG minus VS minus VT. And again, you can take absolute values of those if you want to, but this is an NMOS, so I'm not taking the absolute value anymore. So Vs and Vs cancels out on the left and right. So your Vd, which is on the left, needs to be higher than Vg minus Vt. What is Vg minus Vt? Vg was 3 volts, and threshold voltage is given as 0.7 volts in the previous problem. We're taking the same value. So Vg minus Vt is going to be 2.3 volt. So basically 3 volts minus 0.7 volt. That is going to be the minimum limit of Vd. If my Vd is lower than 2.3 volt, the transistor will not be in saturation. So my Vd needs to be higher than 2.3 volt for the transistor to be in saturation or in the active region. Again, very simple problem. Let's just take a look at the PMOS version of a similar thing. Question.
Oh, we had the general form of that thing. That's very,
So VDS,
yeah, like we're not.
absolute value of VDS is greater than absolute value of V overdrive. That's the general form of active region. Okay. So now what is the question?
Yes, we're not. Does that not matter?
Yeah. So that is already taken care of. You're talking about VDS, right? Whether the transistor is in active region or not, that depends on the voltages at drain, source, and gate terminal of the transistor. It does not. You could have connected another 2 volt here, right? So you only need to consider what is the voltage at drain, source, and gate of the transistor to make sure that you know that VDS is higher than V overdrive or not. Right?
Yeah, but
So
then in this example, we don't consider this work. But
we consider the source voltage, but and why do we consider the source voltage? And that's why your VD has to be higher than 2.3 volt. Why? Because your source voltage was already 2 volts. And then you needed to be overdrive voltage extra on top of that 2 volt, so that your drain potential is at least at 2.3 volt, right? So 2.3 volt is nothing but 2 volt plus that 0.3 volt that you found out in the previous problem. So in the previous problem, you already had VD greater than 0.3 volt if there's nothing connected at the source.
oh, okay. Sorry.
Here 2 volt is connected at the source. That makes it 2.3 volt. Right? So it is already considered. Whenever you're considering VDS, as you saw that the equation that we write is VDS. It already has the source voltage considered, right? VDS is equal to VD minus VS. So VS is already considered in the equation.
It's just, I think it just because of the equation right there, it doesn't, it should be is
So there's no VS here. That's what you're asking, right? But that's just because, yeah, you can calculate your VDS as well. So for example, there are 2 ways to do that. I showed only one. So VDS greater than, let's say, VGS minus VT. I write that first. And because VDS is VD minus VS and VGS is VG minus VS, the VS is both present on the left and right side. So I can cancel out VS and say VD greater than VG minus VT. That's what we wrote here. That's one way to do it. The other way to do it is basically say that my VDS, which is this voltage, needs to be higher than VGS minus VT. Now VGS, what was my VGS? VGS was 1 volt and VT was 0.7 volts. So 1 volt minus 0.7 volt gave you 0.3 volt for the previous formula as well. So this is still the same. VGS minus VT is still 0.3 volt. But what it says is that VDS needs to be higher than 0.3 volt. VDS needs to be higher than 0.3 volt. So what is VDS? VDS is just the voltage between the drain and the source terminal. It's not the voltage between drain terminal and ground, because the source is not same as ground anymore. So if VDS is greater than 0.3 volt, VD is greater than VS plus 0.3 volt, right? Because VDS is nothing but VD minus VS. So VD has to be greater than VS plus 0.3 volt. And VD is 2 volt already that you know. So 2 plus 0.3 also gives you 2.3. All right. Now, if this is a PMOS, then how would it look like? Let's say you have this particular circuit. That you have a PMOS. My current is going into the source. That's how I know it is a PMOS. There is a drain to source voltage. Let's say I'm applying like this. So that's my VDS. Or basically that's my VSD because my source is a higher potential, drain is at a lower potential. So if I take into account the effect of the signs, then that is VSD. But if you don't want to consider the effect of the signs, just take the absolute value and call it absolute value of VDS so that we are not having to change the equations that we learned. This is the absolute value of VGS. Even though this is the source potential and this is the gate potential, so it should have been VSG, but absolute value of VSG is same as absolute value of VGS, right? So you can call this as absolute value of VGS. So in this case, your V overdrive, which is absolute value of VGS minus VT, how much is that? So your absolute value of VGS is 5 volt minus 4 volts. Your gate is at 4 volt, source is at 5 volt. So your VSG is 1 volt, your VGS is minus 1 volt, but your absolute value of VGS is plus 1 volt. VT, that's the threshold voltage of the PMOS. Let's say that is minus 0.7 volt. So absolute value of VT is still going to be plus 0.7 volt. So VGS minus VT is still 1 volt minus 0.7 volt, that is 0.3 volt. Even though VT itself is minus 0.7 volts. And VGS is minus 1 volt, but absolute value of VGS is plus 1 volt. Now, you want to find out when this transistor is in the active region. And for that, we'll still use the same formula. We'll use the same formula that my absolute value of VDS is higher than the absolute value of V overdrive. And we already found out that V overdrive is 0.3 volts, right? So absolute value of VDS has to be greater than 0.3 volt. My VD is this voltage, right? This point's voltage. And this absolute value of VDS is what in this case here? Since your source potential is higher than the drain potential, the absolute value of VDS is VS minus VD. So VDS is negative, but VSD is positive. That means absolute value of VDS will be going to be equal to VS minus VD, as VS is at a higher potential of 5 volt and VD is at a lower potential. So VS minus VD has to be greater than 0.3 volt. So you can write that your VD needs to be less than VS minus 0.3 volt. Just from this previous equation, I can take VS on the right side and 0.3 volt on the left side. So I'll write VD needs to be less than VS minus 0.3 volt, or I can write VD needs to be less than 4.7 volt. So see, in this case, your VD needs to be less than a maximum. Your VD can only be a maximum amount after which the transistor will not be in saturation anymore. So VD has to be less than 4.7 volt so that you have a large drop across the source and drain terminals. Again, the concept remains same, that you want a large drop between your source and drain terminal for the transistor to be in saturation. Remember that the curve of ID versus VDS, your ID versus VDS look like this for the NMOS. For the PMOS, it's the same thing. Just take the absolute value. Absolute value of ID, this will be absolute value of VDS, and the curve will look the same. So which means that the absolute value of VDS has to be larger than something so that your transistor is in saturation, because this is the region when you are in saturation. And for the absolute value of VDS to be larger than something, of course, VD needs to be smaller than a particular amount, a maximum amount in this case, because source is already connected to 5 volts. All right? So that's the only thing that you need to keep in mind when you are dealing with PMOSs, that just take absolute value of all the equations that you have learned till now for either DC analysis or AC analysis. So we are also going to discuss current meters, but I don't think we have enough time today. So we'll start discussing about current meters first thing in Monday's lecture. But let's stop here today. Happy Halloween, and I'll see you on Monday.